maybe put the exercises here. Okay, so first, are there any questions maybe to the what was said in the lecture? So, okay, so maybe let's start with this fact, which says that for any fixed k and d, there are finitely possible types of quantifier rank it should be, let's say, q of k tuples of vertices. Okay, so what does this mean? Recall that if I have a tuple of vertices, k tuple, v1, vk, in a graph, then we can define the type of this tuple, maybe to be consistent with the notation. The type of this tuple in the graph is the set of formulas phi of x1 xk satisfied by a1 ak in G, and formulas of quantifier rank Q. Okay, so we want to prove this fact, that there are just finitely many possible types. So this means that if I take the set of all possible types of all vertices in any graph, so G is a graph, and A1, AK are vertices of this graph, then this set is finite. So this is, it's bounded by some number, it has size bounded by some number n, depending on k and q. So a type is formally, it's a set of formulas. Oh, okay, maybe. Maybe we can start with a simpler thing just to get some intuition about types. Well, okay, maybe let's prove this. This might be. Okay, so to prove this, let's proceed by induction on Q, the quantifier rank. So the base case is Q equals 0, and this is called atomic types of k tuples. Okay, so how many atomic types of k tuples are there? Okay, so I have k vertices, and I want to know what are the possible interactions between those vertices in all possible graphs. But those interactions are described by formulas without any quantifiers, quantifier-free formulas. Okay, so what? Yeah, give me a bound. or a description of those types. Okay, I'll start asking you by name if you don't raise your hand. So, is there any volunteer? Okay, thank you, Michał. Marek, sorry. Go ahead, Marek.
Well, so like there are some equivalence classes, like equality equivalence classes. I mean, some elements can be equal to each other within A1 through AK.
So, okay, so you can have like, we will draw a picture of a type. Yeah, and you mean by, so you can have like x1 is equal to x2 and x3 equals to x4 and let's say x5. We have like partition a partition of x1 xk. So this is a partition which defines, formally this is, well, it's a conjunction saying x1 equals to x2 and x3 equals x4 and x1 is different from x3 and x1 is different from x5 and x3 is different from x4. No, different from x5. Something like this. So this formula is a quantifier-free formula which we can picture like this. We have three equivalence classes of vertices. So there's a partition. Okay, there are many partitions, of course, of k element set. I think it's called, what is it, the Bell number?
Mm-hmm.
Okay, so the number of partitions is bounded by the Bell number. And each partition defines a formula. Like this. Okay, what else do we need? We need to describe the edges.
Yeah, so there can be edges between any pair of these classes.
So edges on parts of the partition. So we can have, for example, edge here and no edge here. So this picture is a partition with 3 parts and 2 edges. And it corresponds to the formula which says those things. And there's an edge from x1 to x3. And there's an edge from x1 to x5. And there's no edge from x3 to x4. Okay, this is one formula. It's a quantifier-free formula, which is satisfied by 5 vertices which look like this. Well, it's satisfied by vertices which satisfy this formula. But the point is that it fully describes a type of 5, quantifier-free type of 5 vertices. Fully determines. So any 5 vertices which satisfy this formula have the same type. Any tuple. So let's say call this 5x1, x5. Any 2 tuples have the same atomic types. So types of quantifier rank 0. Yes, if I have 2 tuples satisfying this, I know exactly everything, which formulas hold between which variables, x1 through x5, which formulas without quantifiers. If you ask me if there's an edge between x3 and x4, then I can tell you, well, no, and so on. So this picture completely defines one type one type of a 5-tuple of vertices of quantifier rank 0. And there are, how many pictures there are like this? Well, we take the Bell number, the number of partitions, times what?
Say 2 to the power n choose 2.
Yeah, 2 to the power k choose 2. Number of graphs on k elements. So this and number of types with 0 quantifiers is at most this number. Okay, so we said every such picture uniquely determines a type, and conversely, every 5 elements conform to exactly one picture of this form. So a partition plus edges on the parts of the partition. Okay, so we did the base case. Now we need to do the inductive step. So what are the types? Types of quantifier rank q plus 1 of k tuples. What are the possible? So we need to find a description of the possible types of quantifier rank q plus 1 of k tuples of vertices. Yes, and we can say, okay, so how do we describe those things? Well, this was this intuition that I was trying to convey. So say let's say we have two vertices, and the type of quantifier rank 1 tells you whether this exists or not. A vertex which is both adjacent to x and y, a vertex which is adjacent to one of them and not x and not to y, a vertex which is adjacent to y and not x, and a vertex which is non-adjacent to y and to y. So we have a picture like this. This is a picture which says x and y are, let's say, different and not equal, and not adjacent. No, sorry. Different and adjacent. And in a picture, we can have some statements of the form like this. So, for example, if we have this exists, this doesn't exist, and this doesn't exist, this corresponds to the formula saying x is related to y. Oh, sometimes I write e of xy, and sometimes I write tilde. Okay, I'll write tilde. And exists z such that x is related to z and y is related to z, and there exists z such that x is related to z and y is not related to z, and there is no z such that x is not related to z and y is related to z, and there is no z such that. Okay, this is a picture where we have bits saying yes or no. Yes, yes, no, no. And in this picture, we also have the relationship between x and y, which is already, yeah. So, okay, so this picture defines a type like this. So it defines a formula like this. And now the claim is that, well, this uniquely determines the type of quantifier rank 1. So this uniquely determines all the formulas with one nested quantifier, which is satisfied by x and y. Yeah, if I want to know, do x and y have a common neighbor? This is determined by this. Do they have a common non-neighbor? This is determined by this, and so on. So any possible formula with one quantifier rank 1 is determined uniquely, its truth value is determined by this formula. Okay, so how to make this more general? And so, for example, we have, how many pictures do we have like this? For two variables, x and y, so k equals 2, q equals 1. How many pictures there are? Well, we have 2 to the 4 possible answers to those questions. And we have, well, at most 3 possible interactions between x and y. Either they're equal, or they're non-adjacent, or they're adjacent. So this shows like n, 2, 3 is at most something like this. If we manage, if we believe that every type of quantifier rank 1 of pairs is uniquely determined, described by a picture like this. Okay, so how do we, in general, how do we describe the types of k-tuples, of vertices, of quantifier rank q plus 1? Okay, the point is that a type can be of a tuple. Yeah, so if I have a tuple of vertices, and I want to know what formulas they hold, are satisfied by this tuple. So I have some formulas, and there's possibly infinitely many formulas which are satisfied by this tuple of quantifier rank q. Let's say q plus 1. But we want to argue that there are just finitely many of them up to equivalence. Yeah, so that's the key observation. There's just finitely many formulas up to equivalence. Of quantifier rank up to equivalence. Okay, it's essentially a restatement of the lemma we're trying to prove. So maybe we can prove this by induction. So let's say we want to show there are finitely many formulas of quantifier rank q plus 1 with free variables x1, xk. So how does the formula look like? It has quantifier rank, let's say, q plus 1. So it can have.
So there are.
Go ahead.
So there are just some disjunction and conjunction of formulas of the form a single quantifier, and after it a formula of rank q.
Exactly. So we have Boolean combinations. So we have conjunctions, disjunctions, and negations of formulas of the form exists z such that psi of x1 xk z holds. Yeah, Okay, and then how do we finish the argument that there's just finitely many formulas up to equivalence? Konrad? So what is the quantifier rank of this formula?
At most q.
Yes, quantifier rank at most q, and by inductive assumption, we know that there are just finitely many such formulas up to equivalence. So in particular, there are just finitely many such formulas up to equivalence. So this is a Boolean combination of at most some number q formulas. Yeah, so there's a bounded number, a finite number, let's say m sub kq of such formulas. And we take a Boolean combination. Yeah, and there are just finitely many Boolean combinations that you can build out of at most this many formulas. So how many give me a bound. How many formulas, Boolean combinations can you, up to equivalence, can you construct out of some m formulas? Say, imagine those formulas are like propositional variables. They can be either true or false. So each of them is, you can think of it as a variable. Okay, maybe that's confusing. Sorry, but I can't. I need a problem with my pencil. Okay. Okay, so how many Boolean combinations? If I have formulas phi1, phi2, and phi3, how many Boolean combinations up to equivalence can I form out of them? Give me some bound. So I can write like phi1 or phi2 and not phi3 and so on.
So maybe we can use the fact that every formula on some m variables can be transformed to, for example, a conjunctive normal form.
Yeah. Mm-hmm. We could do that.
And yeah, and then if we have so, yes, then in conjunctive normal form, there are clauses, and we can compute how many different clauses are there. There will be something like 2 to the power of 2m, I think.
Yeah. Okay. Yeah, this gives some estimate. Another way of saying this, the same thing essentially, is that you can write a truth table. So a Boolean combination of m propositional variables, or a formula, a propositional formula, is uniquely defined by its truth table. So what happens if this holds and this doesn't hold and this holds? And so this is essentially what you're saying. So it's either like this or like this, that phi1 and not phi2 and not phi3. And so as you said, so it's a disjunction of conjunctions. Yeah, and it's essentially, we're specifying the truth table of valid, what happens if phi1 holds, phi2, phi m, and so on. And for all possible combinations, like all those holds, then we give an answer. Does our Boolean combination hold? Yes or no? So let's say psi. What if this fails and this holds, and this holds and this fails? Then our Boolean combination fails, and so on. So there are 2 to the m rows, possible rows in this, and for each possible output, for each row we decide, does the Boolean combination hold for if such a situation occurs, or does it fail? So this what bound does this give? So there are 2 to the m rows, and for each of them we independently decide whether our Boolean combination will hold for this situation or not.
So 2 to the m.
Yes. Yeah, so this gives some crude estimate. It gives 2 to the m on the number. Well, actually, there is exactly this number of Boolean combinations of m formulas if you don't know anything more about those formulas, but there could be some correlations among those formulas. But anyway, this gives us an estimate. Oh, those are formulas with quantifier rank q and with k plus 1 variables. So this gives us our recursion. So m q plus 1 is at most 2 to the m k plus 1 q. So yeah, we can proceed by induction on q, and this gives us some bound, which is, if you expand this will be something like a tower of length O of q. And at the bottom we had something like, we had this number of atomic types, which was Bell number times something global, some function of k, some exponential of k. Okay, so that proves there are finitely many formulas of quantifier rank q up to equivalence. And then, okay, this also proves our fact, because a type is the set of formulas satisfied by A1, AK in G, but we're only interested in formulas up to equivalence, and there's just a finite number of many formulas. There are at most m, k, q formulas. And so a type is just a subset of those formulas, those which are satisfied, and those is, we have a bit vector saying which are satisfied and which are not. So the number of types is at most 2 to the power m sub k q. You can get a better bound where you don't have, we had like this length of 2's was, I think, 2 times q in our proof, but you can have it just equal to q. But that doesn't, well, it's some function of k. Okay, so the number of types is bounded by this constant. And moreover, you can explicitly describe all possible types in all graphs altogether, because we can explicitly construct all possible formulas of quantifier rank q as the set of all possible Boolean combinations of formulas of lower rank. So we can just write all possible Boolean combinations. And then a type is just a subset of all possible formulas. There's an important thing to notice, that so a type is described by a set of formulas. So a type of quantifier rank q and with k variables. So it's described by a subset of formulas phi1, phi k of quantifier rank q and with k variables. So if I have a subset like this of the set of all possible variables, formulas, then this type is uniquely described by, well, it's uniquely defined by this formula. This type can be described by one formula, which says those things are satisfied and the remaining things are not satisfied. So you can define a type by a single formula, as we have done in those pictures here. This type was described by a single formula. But what I wanted to say is it's important to note that even though you can efficiently enumerate all possible formulas which describe all possible types, there is no algorithm which tells you whether such a type is actually realized in some graph or not. It could be that this formula is not satisfiable. So there's no algorithm which tells you if this is satisfiable in some finite graph. So you can enumerate all possible descriptions of types, but some of them will not be satisfiable. And there's no way of finding out which ones are satisfiable or not. It's undecidable. But anyway, there's an algorithm which enumerates all possible descriptions of types. But some of them will be just equivalent to the formula, will not be realized by any tuple, actually. Okay, was the end of a long exercise. And what I wanted to do, okay, so maybe let's do something else. Remember that a cograph is a graph which can be constructed from singleton graphs using edge complementation and disjoint union. Okay, so the goal is to show that we can, given a cograph, compute a term defining it, a cograph decomposition. Let's say, I don't know, do you know what is the best time which can be achieved here? Does anybody know? So I just want you to do it in polynomial time. But can you do this in linear time? Does anybody know?
I think in the lecture it was that like the number of vertices squared.
Yeah, in the lecture I said that it's squared because that's easy. I see how to do that, but maybe I'm stupid and I don't see a easy linear time solution, or maybe there's a difficult one also that I don't know about it. Okay, so let's just first figure out any algorithm. Let's say quadratic or cubic. Yeah, so I'm given a graph. What can I do with it? I want to present it as a, I know it can be presented as a disjoint union of complements of disjoint unions and so on. But I don't know how to do it, so I want to compute this. Okay, maybe first observation. Instead of having complementation, edge complementation and disjoint union, you can have disjoint union and let's say call it complete union, or let's say full union, where a full union of two graphs G and H is obtained by putting them, taking the disjoint union and adding all the complete bipartite graph between them. Okay, so those two things should be equivalent. If you can construct a graph using edge complementation and disjoint union, then you can construct it using disjoint union and full union without edge complementation. Is this clear? Or, and vice versa, so also. Yeah, so how do we do this? So how do we replace fully, how do we simulate edge complementation by full union and vice versa? So I guess one direction is easy. Full union of G and H is equal to, how can I construct the full union using the edge complementation and disjoint union?
So I take a complement of G, a complement of H. I take a disjoint union of those, and I take a complement of that.
Yeah. Okay, that's a full union. And okay, so so this shows that using full union and disjoint union, you can only construct cographs. And conversely, how can we show that cographs can be, all cographs can be obtained this way?
So in some sense, I imagine that if I have a complementation in my like model of the graph, then I want to like push that complementation down the tree.
Mm-hmm.
Okay.
Okay.
And what do I mean actually by that? So what I want to say is that I'm not sure what I want to say.
Okay, so let's try to do this by induction on this structure of the cograph. So the cograph is constructed either using disjoint union, and that's no problem. So yeah, so this can be already constructed using full and disjoint union. So if the topmost node is disjoint union, then we're done, because this by inductive assumption can be reduced. And what about if the top node is complementation? But it's a complementation of a graph, which can be constructed using full and disjoint union by inductive assumption. So we want to show that also the complement of a graph, which, okay, so essentially we want to show that complements of graphs which can be constructed using full and disjoint union are also like that. So those graphs are closed under complements. So claim graphs which can be constructed using full and disjoint union are closed under complements That's what we need to show. Yeah, so why is that?
We can interchange full joins with disjoint unions in the entire subtree.
Yeah. Yeah, replace full unit. So if I have a, like, let's call it, I don't know, this will be the full union. So this can be, to take the complement, to get the complement, we just replace every thing like this by this and vice versa. We swap them. Okay, and this requires a inductive proof, I guess, that this is actually the complement, but this inductive proof is trivial, so the G, so again, we show that the complement of the disjoint union is the same, of the full union is the same as the complement of, I guess this is something like this, which is the same formula that we had previously. And it's symmetric. So this proves it. The complement of a graph which is obtained by those operations is a sum of graphs which can be obtained like this and so on. So those graphs are closed under disjoint unions and complements. So in particular, they contain all cographs. Okay. So we can replace those things one by another, and now we have a given cograph, and we want to compute its term, defining it either using disjoint unions and full unions or disjoint unions and complementations. Okay, so what are the possibilities for G? Yeah.
I mean, so it can have one vertex, which means we are done.
Mm-hmm.
Or it's a disjoint union.
Yeah, so
which means, yeah, it has at least two connected components. In particular, it means that it cannot be a full join because like full joins are connected.
Mm-hmm.
So it means like the only viable thing we can do is to like split the graph into like two separate parts.
Mm-hmm. Well, yeah, there could be more.
Yeah, there could be more. Yeah.
So, okay, so there's this. Yeah, but essentially, we need to argue that if it's a union of several connected components, then we can just focus on each connected component separately, right?
Yeah.
So if the whole graph can be constructed is a cograph, then each of those components separately is also a cograph. Okay.
Yeah.
So if we have several connected components, we can might as well just focus on each of those connected components and then take the disjoint union. So we have simplified the problem to each connected component, which is of smaller size. So why is it the case that if G is a cograph, then each of its connected components is also a cograph?
So it cannot be a full join because like if it were a full join, then it would be connected. Right. And so it must be a disjoint union of like two cographs. And these two cographs of like these two cographs are like a partition of the connected components,
Yes. So
because like there are no edges between those two parts of the cograph.
yeah, so it's like a disjoint union either of those two cographs. Yeah, but we can repeat this argument. So the left one has to be also a disjoint union. So in particular, each of them has to be a cograph, yeah? If each of those connected components. Yeah, because you said that there is some partition into cographs, but then we can repeat the argument with the left disjoint union, and this has to have also a partition into cographs, and eventually we get into, we conclude that each connected component is a cograph. Yeah. There's also another argument. Cographs are closed under subgraphs, induced subgraphs. This is a useful fact. So any induced subgraph of a cograph is also a cograph. Essentially, you take this, this is a tree, which defines your, yeah, okay, this is maybe another exercise. Okay, so each of those has to be a cograph, so we can just focus on each of them separately and find, they're smaller, so we find decompositions of those. Okay, but otherwise, if G has one connected component, then what?
So it cannot be a disjoint union, so it's got to be a full join.
Mm-hmm. Yeah. Yeah, so then we can maybe, so then G is a full, or maybe actually this digression through full joins was maybe it makes it actually not easier, because we can say that then G, then we have to have that GC is a simpler cograph, yeah, because we know that G can be constructed using disjoint unions and complements. We shouldn't have gone through full unions. Disjoint unions and complements, but G cannot be constructed using disjoint union, so it has to be, we have to be able to construct it using complement. So the complement is a simpler cograph. So we take the complement, and we know that the complement must be a disjoint union. Because otherwise we're stuck. If the complement is not a disjoint union and the graph is not a disjoint union itself, then it cannot be constructed using disjoint unions and complements. So we can just take the complement, and it's a simpler graph. We take the connected components and repeat. Okay, so what's the running time of this algorithm? It's polynomial, right? But what is the exponent?
I think something like n cubed in the worst case.
Okay. Damn. Yeah, well, we need to do a lot of connected components, but I think they somehow amortize. I think it might be square, but okay, let's not go into this. Okay, we have 11 minutes left. And yeah, okay, I wanted to do this one exercise to prove this Geifman theorem. Which we probably won't finish. Maybe we can go through this proof of Sezes theorem, because this was a bit vague. How does the algorithm actually work? So we said that model checking is FPT on graphs of bounded maximum degree. And I sketched something, but it was very vague and quick. So here was the sketch. So we're considering graphs with bounded maximum degrees, a maximum degree bounded by D. And one observation was that in such graphs, if you look at isomorphism types of neighborhoods of a vertex V of radius R, then there's a bounded number of those possible isomorphism types. Okay, this was an underestimate. So how many vertices are in the neighborhood? I think something like d to the power r plus 1. So there's vertex V, it's d neighbors, it's d square neighbors of neighbors, and so on. So it's 1 plus d square plus some, and so on. So there's this many vertices, and the number of isomorphism types of graphs with this many vertices is at most, well, something like 2 to the number of possible edges is this choose 2. So this is number of possible edges. Actually, it's much less than that because they have degree at most d. So the number of possible edges is, okay, but anyway, we can have a subset of those possible edges. So this is the number of possible isomorphism types of neighborhoods of a single vertex, neighborhoods of radius r. And the theorem says that if two vertices V and W have equal, well, it's a consequence of the theorem. The consequence of the theorem is that if two vertices V and W have isomorphic, in the same graph, they have isomorphic neighborhoods, then they have equal types. So if this is isomorphic, if those two things are isomorphic, then the type of, and R is equal to something like 2 to the Q. Well, it's, then the type of V is equal to the type of W in the graph G. Have equal types. So that's the theorem. So it says that, okay, there exists an R, for every Q, there exists an R such that if the neighborhoods are isomorphic, so the subgraph of the neighbor induced by the neighborhood of V, together with this distinguished vertex V, is isomorphic to the subgraph around W of radius R, together with this distinguished vertex. So there's an isomorphism which maps V to W, then they have equal types. So this is a consequence of the theorem, of Geifmann's theorem. Maybe we'll prove it later, tomorrow, or sorry, on Friday. Oh, no, Saturday. And now I wanted to conclude Sezes theorem. So that we can do FPT model checking. Or in linear time, we can do model checking whether a given formula sentence holds in a graph or not of bounded degree. Okay, so, oops. here's a formula that we want to verify in the graph. So let's say, yeah. And the naive algorithm proceeds by just enumerating all possible vertices in for each quantifier. Okay, but now we want to be more clever, and instead of enumerating all possible vertices, only enumerate, iterate over all representatives of vertices of a given type. So what do we need to iterate over in the first round? So we have this theorem, consequence of Geithman. And we know that there's a bounded number of isomorphism types. This number of isomorphism types of neighborhoods of radius R. Okay. So the point is that if I have, let's say, Q quantifiers here, nested, and I have two vertices V and W, which have the same type of quantifier rank V, then I don't need to test this formula for both V and W. If this sub-formula holds for V, if the formula holds for V, then it will hold for W as well, because they have the same type, which means they satisfy exactly the same formulas of quantifier rank Q, but this is a formula of quantifier rank Q. So I don't need to check it for both V and W, I just need to check it for one of them. Yeah, so in particular, by the above statement, if they have isomorphic neighborhoods, then they satisfy this, but I only need to check this subformula for one of them. Okay, so what? How do we proceed in the first loop? So we need to iterate over the set of all representatives of neighborhood, our neighborhood isomorphism types in G. Those which are satisfied in G. So we need to iterate over all representatives of isomorphism types. So how do we know, how do we compute the set of all representatives of neighborhood types, of our neighborhood types? Let's just say this and we'll finish. Okay, so what is the running time of an algorithm which computes a set of representatives of our neighborhoods of isomorphism types in G?
So for each vertex, we can compute in f of dq time. It's like equivalence class, identifier, say, where identifier is everything I see in my own art neighborhood.
Yeah.
So like that's a massive key, and then I group everything like by the key, and I take one vertex from each equivalence class. Yes.
So what's the running time of this algorithm?
So it's like f of dq times the number of vertices of the graph, because it's dominated by this like equivalence class computing.
Yeah,
computation.
so for every vertex, we iterate through all vertices one by one, and for each vertex, we do some massive computation, which takes time bounded by d and q only. So we only explore the radius q or r neighborhood of the vertex, but it has finite bounded size. Okay, so we find the representatives, and then we can once we have this, we can proceed with this loop, but only iterating over this set of representatives. And by the way, this set of representatives has itself size bounded by some constant depending on d and q only. This set has bounded size. There's only a bounded number of, well, this number that we mentioned, something like d to the r plus 1 choose 2, many such isomorphism types. So we replace this quantifier which ranges over all vertices of the graph by a quantifier which ranges over a constant number of vertices of the graph. And we can proceed similarly with the following quantifiers. So we have a constant number of vertices to check, and for each of them, we do, again, a linear time pre-processing to do some, well, linear time step to compute some representatives. Now, there's just one caveat. We're looking at neighborhoods of isomorphism types where this vertex x is treated as a constant. So there are isomorphism types which look like this, but there are also isomorphism types which say this vertex is the vertex x, which is already in the context. There's one more constant which appears in, so either the x is somewhere far, or the x is in my graph of radius r. So now we're looking at representatives of our neighborhoods of isomorphism types in G with the vertex x distinguished as a constant. But the argument is the same. And there's still a bounded number of those types and of those and so on. Okay, that's the end of this argument, and sorry for extending over time. And tomorrow, oh, one important thing. Tomorrow's lecture by Michał will be part of a lecture series which is called Friday Afternoon Series, and it will be on under a different Zoom link. So I will send you the Zoom link tomorrow. So there will be a bigger group of people, not only PhD students, but a bigger group of international audience, which will be participating in Michał's lecture tomorrow on TwinWith. So hope to see you there.